Okay guys, so in this lecture we'll be seeing some of the examples in which we need to compare the rate of E2 reaction. So given these two compounds, we need to compare the rate of elimination in both these compounds. One in which Br is attached to the 1 degree carbon, and second one in which Br is attached to the 2 degree carbon. Okay, so what happens is generally we determine the rate of compound undergoing elimination reaction by the intermediary alkene's stability, but in this case, as you can see, the alkene in both the cases formed would be the same one. Okay, so how do we actually compare? So if you look slightly more deeper into the fact that this carbon will actually contain a partial negative charge, and this carbon, and in this case this carbon will contain a partial negative charge when this um, hydrogen atom is removed by the base, which is alcoholic KOH in the both the cases. Okay, and this hydrogen will be removed. Okay, so this will get a partial negative charge here, and in this case this carbon atom will get a partial negative charge. Okay, so but in this case due to the presence of phenyl ring adjacent to this carbon atom, this can actually take place in resonating structures, hence the rate of first compound in elimination reaction would be more than the rate of second compound. Okay, let's come to the second example wherein we need to compare the rate of elimination reaction among these compounds. Okay, so in these compounds, this is the uh, this is the place where halogen atoms are attached to the carbon atom. Okay, so in this case the double bond can be formed either here or either here. Let's say the double bond is formed here, then it would have only 4 plus 1 5 alpha hydrogen, but if the double bond is formed here, it would have 8 alpha hydrogen. So the major product would be having 8 alpha hydrogen in this case. Similarly, major product in this case will be having 5 alpha hydrogen, and in this case the double bond would not even take place, and the elimination would not even take place. Why? Because of the violation of Brett's rule. Why? Because if we have a double bond here and this hydrogen attached here is taken by the OH minus, and we have a alkene character across this carbon atom and this carbon atom, then this will have a sp2 character, and the carbon which is the bridge head in case of Brett's rule cannot have sp2 character, hence the stability of 1 would be more than 2, and third won't even participate in the elimination reaction, so it would be the last. Okay, let us consider the case for this. Okay, so in this case also we have no alpha hydrogen attached on this alpha carbon, hence elimination reaction would not take place here, because the incoming OH or OH from the alcoholic KOH group cannot actually attack on alpha hydrogen. Hence in this case elimination reaction won't even take place, hence the rate of elimination in second compound is more than the rate of elimination in first compound. And the second compound, obviously I have alpha hydrogen attached here, so the product would be formed something like this. Okay, similarly in this case we have two CH3s coming out of the plane, and including this Br which is coming out of the plane, and in this case two CH3s coming out of the plane and Br is going inside the plane. Okay, so we can actually have the anti elimination, because from any of these two hydrogen atoms are actually anti to the Br, as they are going inside the plane and Br is coming out of the plane. Hence we can have a double bond character across in this compound, and it will show elimination reaction, unlike in the second compound wherein we have Br attached here, and in both the cases hydrogen would be going inside the plane, and in this case also hydrogen would be going inside the plane, hence Br cannot actually form or eliminate itself to create a double bond with any of the adjacent alpha carbon atoms. Okay, what about this compound? So in this compound also the same theory goes, as if the elimination of this alpha hydrogen takes place, we'll have a double bond character across this, and it will form a aromatic ring. Okay, so hence one the highest stable, then comes second, then comes third, because in second at least we have a conjugating structure, resonating structure, because of the conjugate double bonds, hence 2 would be more stable than 3. Okay, in this case, if we form the double bond, then double bond will come across this carbon atom and this carbon atom. In this case, and in this case it will come between these two, and in this case it will come between these two. Okay, so just calculate the number of alpha hydrogen. I think the number of alpha hydrogen in the first case would be the highest, in the second one, and in the third one we have 0 alpha hydrogen. Hence the rate of reaction would be of this order: 1 greater than 2 greater than 3. Okay, now actually let us look at some more interesting problems. We have something like this, where we have to compare okay, which is a better base than in the 2. Obviously 2 is more than 1. Okay, and let us compare the rate of elimination reaction in these compounds. We have something like this. Let's say we have Cl here, Br here, and CD3 and Br. Okay, so if you look at the leaving groups in all the cases, so I think the order would be, as iodine is a very good leaving group, because the I minus is more stable than Br minus, which is more stable than Cl minus, which is more stable than F minus. Hence first would be the having the highest, then comes the third. And in this case, if we look at the CD3 bond, we know that the CD bond energy is greater than CH bond energy. Hence breaking up of this bond will actually require more energy, hence the rate of reaction would be low. Okay, hence 1, 3, 4 and 2 would be the order. Okay, this is a good example. Let's come to the next example, wherein we want to compare the rate of reaction between these two simple products. So what would the rate of reaction here? Okay, the rate. So if you just look at this, in this case we have only the coming base also have more steric hindrance at this carbon atom. Okay, and also less options, as because in this case OH can directly either go to this carbon atom or this carbon atom, and also steric hindrance is less, hence rate of 1 would be more than 2. Okay, so now we are looking at another question in which we have to tell the total number of E2 products formed in the reaction. So total number of E2 products formed. Okay, start off with the first example. We have something like this. CH2, CH3, and here we have. So what is the total number of E2 products that can be formed? Obviously one is something like a double bond here, another is double bond here, and another is double bond here. Okay, is there any other possibility? No, then 3 is the answer here. Okay, let's look at this compound. Yeah, something like this. We have VR here. Okay, so what is the total amount of products which can be formed here? Obviously one double bond can be here, one can be here, and another can be here. So total number is 3 again. Let's look at the third example. We have 1 bromobutane. Okay, so answer would be 1, but obvious. We have 2 bromobutane. So what would be the answer in this case? Let us draw. We have 2 bromobutane. Okay, so one possibility is we have something like this, another is we have something like this, another we have something like this. Total 3 products are formed, including stereoisomers. Okay, let's look at the last example in this video lecture. We have something like this. So what would be the total number of products? Answer would be 2. How? We can have products like this one, or we can have products like this one. Okay, so with this we come to an end of this lecture. I hope you have enjoyed this lecture, and we'll meet in the next lecture with a set of more examples. Okay, till then, good luck and goodbye.